To tech or not to tech? That is the question. Well, when it comes to SWIR cameras featuring Sony's SWIR in-gas sensors. Specifically, LUCID's Atlas and Triton SWIR cameras. I'll talk about these two cameras, how they're the same, how they're different, and some tips on managing heat. Before we tackle the differences, I think it's important we first go over the similarities. To start, they both use the same Sony sensors, the 1.3 megapixel IMX990 and the 0.3 megapixel IMX991. Both cameras are built to our factory tough specifications, meaning they go through active sensor alignment during manufacturing and are certified against physical shocks and vibrations. They have EMC industrial immunity and both offer IP67 dust and water protection. They each have robust M12 and M8 ports, and they both use 1 gigabit Ethernet. So, on to the major difference. Why are they different sizes? It comes down to cooling. The Atlas SWIR is larger because it employs an internal Tech 1 device attached to the sensor, Tech meaning thermoelectric cooler. It also has a large internal heatsink connected to that Tech, and that in turn is connected to the Atlas case. The Tech and heatsink pull the heat generated by the sensor away from it, with the heat dissipating on the larger surface area of the case. Managing heat from the SWIR sensors is very important because more heat will negatively affect imaging performance. That's why our engineers designed the Atlas SWIR at this size. This size allows the SWIR in-gas sensor to operate at a consistent 15 degrees Celsius, resulting in low dark current, less noise, and overall better and consistent imaging quality. As you might have guessed, the Triton SWIR doesn't have an internal Tech or large internal heatsink. This is what allows the Triton SWIR to be more compact and more cost effective. So what does this really mean to you? It comes down to how you plan to use the SWIR cameras. If you only plan to trigger the camera from time to time to capture a few frames periodically with very short exposure times, then the Triton is a good option for you to take a look at. Granted, it should be mounted to a good thermal conductive platform, and potentially other cooling devices should be considered. More on that later in the video. If you do want to run the Triton SWIR for longer exposures or for 24/7 streaming, you'll need to implement your own heat management design. To show you more detail on how heat can affect the SWIR sensors, we did some tests. Using EMVA 1288 performance tests, thanks to the tech and cooling design of the Atlas SWIR, dark current is 7 times less than the Triton SWIR. During the test, the temperature reading on the Atlas Tech was at 15 degrees Celsius, while the imager board on the Triton was reading at 35 degrees Celsius. Dark current is strongly dependent on temperature. To illustrate this more, we took a hot cold plate device and placed the Triton SWIR camera on this device, cooling the temperature case of the Triton to 10, 20, 35, and 50 degrees Celsius. Here you can see those case temperatures and the resulting sensor temperature and dark current data. The higher the temperature, the worse the imaging quality was, with dark current doubling every 7.7 degrees. Dark current matters because it uses up some of the saturation capacity in the photodiode, reducing the available full well space for measuring light. With reduced saturation capacity comes reduced dynamic range as well. Expanding on the previous chart, here we can see how the increase in dark current negatively affects dynamic range and the maximum exposure time before you reach a 50% reduction in dynamic range. Cooling a Triton SWIR camera case down to 10 degrees allows a user to have an exposure time of up to 17.5 seconds before you experience a 50% reduction in dynamic range. This is about the same operational result as the Atlas SWIR with Tech. On the other hand, if you let the Triton case heat up to 50 degrees Celsius, you'll have less than half a second before your dynamic range is reduced by 50%. In other words, the dark current will completely fill the photodiode well with a 1 second exposure time, as the dark current at that case temperature will match the saturation capacity of the SWIR sensors. In addition, the more dark current and longer exposure time, the more read noise increases as well. So if you want to maximize imaging quality on the Triton SWIR, we'll need to think about cooling. Some tips would be when you're mounting the camera, don't use rubber or stainless steel. Mount it against a material such as aluminum or copper or any other material that has high thermal conductivity. You can of course attach your own heat sinks or other cooling components to the Triton case. Or you just have to remember to operate the Triton SWIR with very short exposure times. Now with the Atlas SWIR, you don't need to worry about any of that. The Atlas SWIR, you get a Tech 1, a large internal heatsink, and a camera engineered to not only properly dissipate heat, but also an internal camera design with comprehensive power regulation and cooling to maintain optimal image quality throughout your streaming. With the Triton SWIR, you'll have to manage the camera's heat on your own, but you get a much smaller camera at a lower cost. So that's the end of this video. I hope you found this video insightful. Thanks for watching and stay lucid.